far, we've been just talking about the preface, right, or introduction to it. So where were we? I think we derived the equation of motion, right? Is that how much we covered? Okay. So basically, if I can quickly summarize, as long as we can find a basically coordinate system, a single coordinate can describe fully the behavior of that motion, right? An independent coordinate system that can describe the behavior of that motion, okay? We call that a single, we can consider this as a unit or the single degree of freedom system, or the behavior of the system can be described in terms of that coordinates, okay? So we talked about that, and then we said, okay, if you have a single degree of freedom system, what it means is basically you do have a mass that when it is acted upon by a disturbance, a time-dependent force, its motion is resisted by an element which we call that a stiffness element. Since the motion takes place only in one direction, it's translational, and we're assuming it's linear. Therefore, this is basically a spring, okay? So if this is going through a displacement, okay, mass goes from here to here, it is displaced this amount, u of t, the displacement that this element goes through, okay, or the force that this is generating, this linear spring, would be K times U. K is the stiffness, okay? And then there was another force, okay, that we said, okay, we cannot fully physically, of course, describe that, but we call that a damping element. And we said that the force that is generated in this damping element would be proportional to the velocity of the system. And this parameter of proportion is called damping coefficient. So this one we call damping coefficient. And this one we call the stiffness coefficient. So based on this schematic representation, which is a single degree of freedom representation of a physical system, as long as we can set up this single degree of freedom system, we said that, okay, we look at its dynamic equilibrium, and in order to look at the dynamic equilibrium, this is what we do. We put the lumbar force or the inertial force in the opposite direction of motion. We draw the free body diagram, which consists of this force, and this force, and that force. And out of all these forces in the direction of motion, so you get mu double dot plus cu dot plus ku is equal to f of t. We said this is called equation of motion, and the objective of this course is to not just solve this equation, but understand that, what that solution means. In order to understand that solution means, first of all, this equation has all the information about the system. In order to set up this equation, the first and foremost important step is to be able to model the system. Modeling the system means to find what is this equivalent mass, what is this equivalent damping, and what is the equivalent stiffness in the system. We will see that. Okay, and the second is to be able to solve that. So mechanical vibration comes down to basically two important tasks that we will carry out in this course. Task number one is how to model a system as a single degree of freedom model. In other words, if you're given a physical system, how do you identify or derive its equivalent mass or its damping and its stiffness? So that's objective or task number one. Task number two is solve to find the response. In other words, when you solve this differential equation to find the displacement or velocity or the acceleration and so on, okay? So these are the objective of this course. We will spend quite a bit of time here because setting up this single degree of freedom system or the model is really the essence of, setting up this equation and solving the problem, and idealization. So we're going to spend quite a bit of time here, and that would also help us really understand what it means to set up a different, single degree of freedom model of a physical structure. Then we, of course, once we have done that, we look at the behavior of this under the action of forces. In order to do that, basically we consider several cases or categories. Category number one, or case number one, is that we assume that the system that we are given is such that we can actually ignore that damping. So we call that undamped system. And case number two is we cannot ignore the damping. We call that a damped system. So we look at the vibration of both damped and undamped system. And in each case, we look at basically two possibilities. Possibility number one is the system has been disturbed due to a force, but the force has disappeared now, so it's vibrating freely on its own. We call this free vibration. Case number two is the system is vibrating under the action of an existing force, that is dynamic force, that is disturbing the system. And in this case, we consider three possibilities. Either the external force is harmonic or periodic, or in general, like an impact load or blast load and so on. We do the same thing for the case of damped system vibration. First, we look at free vibration of a damped system, and then we look at the forced vibration of a damped system. So that's it. That's all we are going to do, and of course in many details. Okay? So with that said, let's just begin. We are going to start with the free vibration of undamped system as the first case that we are going to look at. But not only that, in fact, that case sets the tone for the rest of what we need to do. In other words, from that analysis, we identify the key inherent quantities that are important in a mechanical system, okay? So this is what we are going to do. We are going to assume that the damping is zero. Therefore, the equation of motion will reduce to something like this, okay? Or basically, you have a system that only consists of a stiffness and a mass, okay? Subjected to a load, that this load has caused the vibration, now has disappeared. So how do you solve the second order linear, homogeneous, innocent looking differential equation? Do you remember that? Anybody? I'm not gonna go to the details of that, but what you do, you set up the characteristic equation. You find the roots of the characteristic equation, and the solution of this differential equation U is the sum of those two. Okay? The characteristic equation for an equation like this would be what? M delta squared plus K is equal to 0. If you remember from the differential equation, I'm not going to get into the details of that. Lambda is an exponential function, so you assume a general exponential function, substituting that, equate that to 0 and so on, it results in this. So from here you need to find the roots of this, that is lambda 1 and 2, which obviously you can see would be complex, would be plus and minus I square root of K over M. So solution now to this differential equation, okay, would be U1 and U2, there will be two values, have two responses, two solutions. U1 is C a constant times e to the lambda 1 t, or C1 to the e times I square root k over m t, and this is C2 times e lambda 2t, or C2 e to the minus I k over m t. The solution is the sum of these two, U1 plus U2. That's a general solution. So would be C1 e to the I k over m t plus C2 e to the minus I over k over m t. You remember from Mr. Euler that complex number can be written in several forms. One was this, the other one was r e to the I theta, and this is equivalent to r times cosine theta plus I sine theta. So this form is not that desirable, so I'm going to convert that into this form. So I can write this as then C1 times cosine of k over m t plus I sine of k over m t plus C2 times cosine of k over m t minus I sine of k over m t. So let's simplify that by factor out the common terms and do all the additions and whatnot. So if you do that, you can simplify this. U would be C1 plus C2 cosine of k over m t plus C1 minus C2 okay, I times sine cosine k over m t. These are just some numbers or constant values, this and this. So I can just call this A1, this one called A2. So U then can be written as A1 cosine of k over m t plus A2 sine k over m t. If you look at this function, it's simply a harmonic function. or sinusoidal function, right, whose frequency of this oscillation is this, which I'm going to call that omega n k over m. But what is this frequency? This frequency is so unique, meaning that it is a function of two inherent characteristics of the system, being the displacement and the mass. Every system in the world, any physical structure or mechanical system, has its own stiffness, a unique stiffness, right? And unique mass. So these are inherent or the natural characteristics of the system. For that reason, we call this natural frequency. Natural frequency is almost like an ID card for any physical system, okay? And of course, as we will see later on, we call this fundamental natural frequency because we modeled the system as a single degree of freedom system, okay? So the understanding of this is important, is the first building block of whatever we do in the future, so bear that in mind. As I said, this is a harmonic excitation, okay? So this is a general solution. So let me rewrite that now that we have defined natural frequency. U then would be A1 cosine omega nt plus A2 sine omega nt. We have these two constants. How do we find those constants? So we have the specific solution. We need some initial conditions. We need two initial conditions to find the two unknown coefficients. So let's say if at some time, say time equal to 0, I have the value of the displacement, u at time 0, which I call that u dot, u naught, and the value of the displacement at time equal to 0. So this is u bar naught, value of the displacement at time equals to 0. I call that u bar dot naught. Okay. If you have these two, we can find these quantities, right? Because if you substitute here for u at time equal to 0, right? That means left hand side is u at time equal to 0. This is going to be 1, A1. This would be at time equal to 0 would be 0. So A1 then is u naught bar. If you take the derivative of this, u dot would be negative omega n A1 sine omega nt plus omega n A2 cosine omega nt, and equate time equal to 0. This would be 0, this would be 1, so and u dot at time equal to 0 is u dot bar naught. So this would be omega n A2. Therefore, A2 then would be u dot bar naught divided by omega n. So you can write this equation in terms of the initial conditions, and that is another alternative form. So in other words, u of t is equal to u bar naught cosine omega n t plus u dot bar naught divided by omega n sine omega n t. So this is the same equation in terms of the initial conditions. Okay? Let's look at this further, see if we can further simplify this, because I want to show you that this is actually just a single harmonic function. You may not see that, you may not believe me that sum of two harmonics is a single harmonic, so let's show that. Let's assume that here I take this and multiply this by a quantity A1 squared, A1, A2 squared, the square root of that, and divide it by that same value. In other words, this is A1 divided by A1 squared plus A2 squared cosine of omega n t plus A2 over that sine omega n t. Haven't done anything, right? I've just multiplied everything by 1, because they cancel out, right? But by doing that, now I can look at these two coefficients, this one and this one. If I call this alpha, this is beta. You can see that alpha squared plus beta squared is 1. There are two functions in the world that if you square them and add them together, the sum is 1. And that's a sinusoidal and a sine and cosine function. So that means A can be assumed that it is the sine of a number, sine of a quantity, and this is the cosine of some number. Or it can be cosine and sine, doesn't matter. So now remember the trig identities. Do you remember sine theta, cosine something, cosine theta, sine something is what? If I call this A, I can write this U as A times sine of omega n t plus theta. The reason I said that, let me remind you, sine A cosine B plus cosine A sine B is sine of A plus B. That's where it comes from. So this is an alternative form of the same thing. So the response of a system, a single degree of freedom system that is undamped, is a harmonic function, okay, where A is the amplitude, omega n is the frequency, and theta is the phase angle. We'll see that in a minute. But what is the amplitude? Amplitude is the maximum value of dynamic displacement, right? Because it's a sinusoidal function. So what is the maximum value of a sine? 1, right? So if you have a free vibration of an undamped system, you can find its maximum displacement. That is the value you use to find the maximum stresses and whatnot and so on. So let's just quickly look at this, because as I said, this is not mathematics. This is not a course in differential equation. Our aim is to understand the solution physically, what it means, what is the implication, not just coming up with a mathematical solution. Okay? Any questions first before I erase this? Everything is easy so far. Okay. Okay. If you plot that function, this is how it's going to look like. You can definitely plot that much faster than I can. On a click of a button on your calculator, right? To set it up. But this is what it is. If you plot U of t, this is how it should look like. And that is how a free vibration of an undamped system is. So I'm going to plot U versus omega n t instead of t. So this axis is U, or the displacement, that is omega n t. that function means it is a sinusoidal function that has a phase angle. That means it lags an angle theta. Okay, I can do a good job here. So I'm going to extend this just a little bit to do the justice I need that. Okay, so that's how this is going to be. It's a sinusoidal function that is lagging an angle theta compared with just a pure sinusoidal function. Yes?
I have a question a little bit back.
Sure.
When you kind of lumped the I, no, for A2, you kind of put the I into the A2 term.
Right. It's a number, right? At this point,
well, isn't it an imaginary?
it is, but imaginary is a number.
But then, like, aren't we plugging in the real number
Well,
down there?
this, in other words, A2 has some imaginary component in it, but at this point we don't care.
Okay.
We just assume it is a quantity, and then we demonstrated that that quantity, right, in fact, is going to be this if we have the initial values. Right, we'll see that. Don't worry about the complex issues. We will see that, what that means, in fact, later on. So, but this is lagging, theta behind a sinusoidal curve, okay? There are a couple of things, observations that are important, right? This vibratory motion is sinusoidal, that is repeating itself every t seconds. And t is what? Called a period. At every single t, which is a period, it just repeats itself. This is the maximum value or the minimum value, which would be the same in terms of absolute value of it. So this is basically, it is a sinusoidal function, so the distance between the two zeros or the two peaks are the period. And this is basically pi over 2, pi over 2, pi over 2, pi over 2. The total period is 2 pi for a sinusoidal function, right? So at this point is where t, where you have t is equal to 0, right? So this is the initial velocity, or I showed that actually by this symbol, right? And this is the slope of this, which is the derivative of this curve. This represents the initial velocity, right? Initial displacement, initial velocity. If you plot the derivative of this, which is the velocity curve for the velocity response, right? I should have left more space here. What do you see? So if you plot now u dot of t, still has that phase angle, but you know that this curve would be maximum where this one is 0, would be 0 when this one is maximum. So at this point, this should have a maximum. So it looks like, I'm sorry, it should be 0. So it looks like this, okay, versus, okay, this is maximum. Where this one goes to 0, this is maximum. Where this one is maximum, this goes to 0, and so on. So it looks like this, right? So same. So at this point, right, which is time is equal to 0, this is your initial velocity, okay? And if you consider the slope to that curve, would be your initial acceleration. So you can also plot the acceleration curve so you can see all these differences. But you can also get more information from here. In other words, for instance, what this curve tells you, when the displacement goes to 0, okay, it takes a time, right? This is 90 degrees or pi over 2, whichever that you consider. It takes a time that is omega nt is equal to pi over 2, so you can find the time t of, say, 90 degrees over omega n. It takes this much time. After this displacement is 0, the velocity becomes 0. Okay? A lot of things that you can read from these graphs and get from that. And obviously, when displacement is maximum, velocity, which is a cosine function, is a minimum, and so on, which you remember from trigonometry. You know, you have a cosine function and you have a sine function, right? This is a sine, this is a cosine. So when this is maximum, this is 0. When this is maximum, this is 0, right? You're going that way. Okay. But anyway, the important thing is this. There are 3 things we want to summarize from this free vibration, which will help us with the next step, which is modeling. Number 1, we fully understood, or I hope at least, we fully understood that this motion repeats itself, okay? So I would write that as the characteristics of this behavior of the system. Number 1, at every t, okay, t going to t plus t, where t is, of course, is 2 pi over n, okay, 2 pi over omega, and this motion repeats itself. That's the meaning of a harmonic motion, right? The frequency of this motion is what? K over m, and of course, in this form, its unit is radians per second. We introduce another sort of a unit of writing the frequency, and that is omega n over, if you divide that by 2 pi, and we call that hertz. Okay. So that's the natural frequency, or the frequency of this oscillation. Now we make an observation, which is kind of interesting to, especially when it comes to some practical cases. How do you find the natural frequency? Well, of course, if you know the stiffness, you know the mass, you can find the natural frequency, but that's not necessarily easy at times. You're not given those values. It's not easy to find those. So let's see, are there ways that you easily find this? I'm going to rewrite this equation in a different form. Let me write this in this form. Omega n, okay, is what? K over m. How about if I replace m with its equivalent? What is a mass? Mass is weight divided by the acceleration of gravity, right? So if I substitute it there, I have K over W, right, times G, right? So that becomes the equation. But what is the meaning? Or let me write this also in terms of the Hertz formulation. But before doing that, let's look at this. What is K over W? What is W over K? W over K, what does that mean? If you have a beam with a lumped mass of W, in other words, the total mass of the beam is lumped here. What is this? That's the static displacement of this structure under its own weight. So W over K means the displacement of a system under its, due to its own weight. Is a static quantity. It's not, has nothing to do with dynamics or vibration, right? So if I substitute that in here and I write it in terms of the Hertz, I will get 1 over 2 pi times G over the static displacement. Or I can further simplify this. I can write this as G over 2 pi times 1 over the square root of that static displacement. In English units, G, the value, if you substitute for that, it happens that if you substitute this value, evaluate this, it comes out to be almost 3.14, which is almost pi. So we can write this in a nice form, and this becomes an equation that you can use to easily find the first natural frequency of the system. Yes?
I had a question about the second graph.
Right, right.
Is that supposed to be the derivative of your top?
It is a derivative of the top,
Okay,
yes.
so you
Yes.
did the negative derivative, I was just curious.
You mean here?
No, your bottom graph.
We're here? Well, it can be.
It can be the negative or positive?
Sure, right, yes, absolutely. Because, you know, if you have sine function, you take the derivative of that, right? It's a cosine function, cosine. You're talking about the phase angle, right? Right, that's what I guess you're talking about. Okay, so, yes.
It is only for English unit, pi over.
Yeah, it is not just for the English unit. So in the English unit, the equation somehow comes out to be pi over square root of this, right? But formulation is basically this,
Okay.
right? Now, what does this tell us? It tells us you can find or have the static displacement of a system under its own weight. You can find the natural frequency. That's a very easy, simple, and straightforward way for approximating the natural frequency. This reminds me of a problem many years ago that there was a offshore company. They were going to design an offshore platform. Okay, so they had approached, you know, some people, consultant, whatnot, to find out, if, you know, if it is safe in that whatever sea, given the ocean waves that have certain frequencies and so on, it is safe to design this. Natural frequency is a very important quantity, as we will see later on. One of which is, as we will see, the concept or phenomena of resonance. If you have a forcing function, harmonic forcing function, that its frequency is the same as the natural frequency of the system, this response, we will see, is going to grow to infinity. In other words, displacement would go infinite or the system fails. That's what it means. It's called resonance phenomena. We'll talk about that. So these guys were not sure if it is safe to build that in that environment, right? So they wanted to basically do some rough approximation. They didn't want to spend much money either. So they had approached someone and that someone had told them, okay, I can do this. I can set up a nice finite element model and give me all this stuff, and then, you know, I can do the analysis and give you that. They wanted this something quick. So I said, you know, wait a minute, we don't have to do that. You know, what is this? This is just, you can model this as a simple cantilever beam, right? This is a column, right? A structure, steel, whatever. This is a cantilever beam. You can find the stiffness of that. You have the, you know, mass moment, I mean, you have the moment of inertia, you have the modulus of elasticity. You remember from statics, right? You can find the stiffness of this, 3I over L cubed, the cantilever beam. So if you have the stiffness, right, of this beam, and you know what is this weight of this platform, which you should be able to, I mean, they give you all that data, right? Let's say that W divided by K gives you a value of whatever that is, maybe, I don't know, 3 feet, whatever that is. Just substitute that in here, you immediately find the natural frequency. You don't have to do a sophisticated analysis as a rough approximation. In fact, when you go to the lab, if you're doing an experiment, given a beam or whatever, you want to find the natural frequency by looking at the signal and this and that, you can first do a crude approximation by having the weight of that beam, right? Having the stiffness, if it's a cantilever beam, you have clamped it at one end, you're vibrating it, is a cantilever beam. Assume that the entire weight is basically at a single point, being the tip of that. So calculate the static displacement, which is the weight divided by the stiffness, use this formula, find natural frequency, and then compare that with the experiment. So the point is that, you know, these are the important sort of the pieces of information that we have extracted by just studying that simple motion, which is the free vibration of an undamped system. As you will see now, the next step is we're just going to focus on what we've learned. We know what is the natural frequency, we know what is the stiffness. So the next couple of weeks, we're just going to focus on how to model a system as a single degree of freedom system. 2 or 3 weeks we spend on that, then we go to the next step. Have a great weekend.